Welcome. In this video I'm going to show you how you can obtain Johnston-Berry-Mieke E using Python, which is an effect size measure that could be used for a chi-squared or likelihood ratio goodness of fit test. I'm using a standalone version of Jupyter Lab and I'm running, let's check, Python kernel 3.8.13. But this should work with most versions of Python 3 or from Python 3. So these are the formulas. There are two, one specifically for chi-square test and one for likelihood ratios, or g-test as they're sometimes referred to, a wild test if I'm not mistaken. Um, and unfortunately they don't give a rule of thumb for the interpretation, but you can actually calculate another effect size, Cohen's W. You can convert the E to one of those Cohen's W's, and Cohen did give some rules of rule of thumb on the interpretation. To show you how to calculate all of this with Python, I need an example file, so I'll import pandas. If you've never used pandas before, you probably need to do a pip install pandas first. Then I can load some data in. I'm loading GSS 2012, which is General Social Survey from 2012, and I adjusted it myself a little bit just for the purpose of these explanations. The first 5 records, as you can see, there are 706 variables, columns. I don't need all of them. I only want to look at the marital field, so mar1 was that, and do an immediate count of how often each of the categories was chosen. So for example, 181 people chose widowed. Now to go over this whole formula, there are a few things we need. The first one to perhaps focus on are the PIs. Those are the observed proportions. So that's simply actually all of these counts divided by each of them divided by the sum of all of them. So the sample size. I can simply use sum to get the sample size and then say, well, I want you to divide each of those counts by that sample size. So these are my my observed proportions. Then Qi in the formula is the expected proportion. Now, since I'm going to simply assume that each category was equally likely to be chosen, this is simply 1 over k for each of them. K is the number of categories, so you can get that by saying, well, how long is this? Well, it's 1, 2, 3, 4, 5, so that should give me 5. And then do 1 over k as an array and multiply that k times so that I get 5 times that expected proportion of 0.2. So all of these indeed sum up to 1. Finally, we need Q itself, which is the minimum out of all of these, which is a little bit redundant because they're all the same. So that should also be 0.2. Now this was that big scary looking formula, but we have everything we need. Q over 1 minus Q, so that's this part. Then a big summation sign, so there's a sum of the proportions squared. Squared can be indicated with a double asterisk, divided by the expected proportion, and then minus 1. So this should give me the result, which is in this case 0.16. There's an alternative way of calculating this, which is by using the chi-square value, the minimum expected count, and then the sample size. Now, I have separate video and notebook on how to actually calculate this chi-square value, so I'm not going to repeat all of that. I'm just going to quickly calculate it using scipystats chi-square function. And then I also need the minimum expected count, which is simply my expected counts are going to be 1 n over divided by k, and then again I need that 5 times, and then get the minimum out of those. I actually could have just done n over k because the expected count should be the same for each of them. Now, if in my case, but if you have different expected counts, then so if your expected counts is really a list of different counts, then this will work as well. now I can plug everything into that formula, and that should give me the same result. Now to convert it to Cohen's W, I'll simply take my found E and multiply that by 1 minus that Q divided by Q, and then all of that has to be, the square root has to be taken from that, which is the same as raising something to the power of a half. So in this case, Cohen's W would have been 0.80, and using some interpretation we could say that's pretty large. For a likelihood ratio test, the calculating E is slightly different. We do need the log function, the natural log function, which is actually in the math library from Python, and log will actually return the natural logarithm. I need to loop over each of them because I can't just plug all of them in one go, unfortunately. So I loop over all the categories and calculate this sum bit one by one, which is then the proportion, the pi, multiplied by the natural logarithm of the proportion divided by the expected proportion from that category. After it's summed up all of these, it still needs to be multiplied with this, so that's the minus 1 over the natural logarithm of q. Also so this turns out to be about 0.18. Alternatively, you can use the chi-square value from the likelihood ratio test, or g-test. Again, I have a separate notebook on how you can actually obtain that. Here I'm just quickly using the power divergence, which will give me that test statistic. I already have everything else, so it's the statistic divided by 2 times n, that's this part over here, and 1 over ln, the natural logarithm of q, so that's there with a minus in front of it. All of this I could have done in one function, so here I made a small function of my own where you feed it statistics, the chi-square value, the minimum, which is either the expected count, the minimum expected count, or the minimum expected proportion, depending on if you want to do the chi-square test or use the likelihood ratio test. And then it just calculates E, and we can test if it works, which seems to be fine. Alright, so that's how you can calculate this Johnston-Berry-Mieke E using Python. Hope this video was helpful. Thank you for watching.